All right, welcome everyone. So today we're going to talk about the Vital Bracelet series. There's a lot to cover, so let's get started. All right, so the Vital Bracelet is a series of fitness bracelet toys sold by Bandai from 2021 to 2024, and it puts characters you can raise on your wrist, starting with the Digimon on the Vital Bracelet Digimon and Digivice V, to tokusatsu characters with Vital Bracelet characters, and finally a number of anime series on the Vital Bracelet BE. So by doing exercises and battling, you can put your character on different paths to evolve into other characters. All right, so the main gimmick of the ecosystem is the ability to download content from cards called DIMMs, or Digimon Identified Memory. These are flash chips mounted on PCBs with a micro SD pinout. There's also device-to-device battling using a special card called a VSDIMM, which copies data from one device to another so they can battle with each other. There's also a few apps. They're for storing characters and battling online, and they use NFC to communicate with the bracelets. So here's the inside of a Vital Bracelet. Here's some of the hardware that's inside the first generation, which covers the original Digimon version and Digivice V versions. Despite the different releases, this generation all had mostly the same innards. So the main chips here are the big circular one is actually a COB, so that's a microcontroller. It's a General Plus GPC 4P096UA. It's a 16-bit microcontroller on the micro NSP architecture. And then we have in orange the flash chip, which contains most of the code and the resources. It's a Micronix chip, 16 megabytes. Further to that, we have NFC tag. It's an NXP Intake I2C+, and there's also accelerometer, heart rate sensor, and the usual power stuff. Interesting thing to note about the accelerometer is the first one used the Bosch accelerometer, but they replaced it on a second production run without changing the PCB to a different accelerometer, but same pinout, different registers. All right, aside from these chips, there's also a color LCD display connected over SPI and a NFC antenna overlaying it. Okay, so on the color LCD toys, there tends to be a discrete flash chip for storing images because each color image is around 16 times the size compared to black and white sprites. So this helps us because there's also usually programming on these chips instead of everything being inside the chip on board. So to dump flash chips, you'll need a flash programmer, and then either you use an SOP8 clip, or you desolder the chip and put it in a socket. So for desoldering, you can use desoldering alloy and also hot air, though if you use hot air, be careful because it tends to melt plastic, so make sure to mask everything off if you're doing things in place. For the SOP8 sockets, there's 150 mil and 200 mil widths. So if you see the chip is a little bit narrower than usual, that's probably 150 mil. Make sure you have the right socket or buy both. All right, special word of warning. So the CH341 programmer is cheap and plentiful, but also sort of dangerous. So the main problem with it is, well, first, it's very slow. It takes minutes to read each chip. It also has some of them have a bad board layout, so instead of 3.3 volts, it's feeding 5 volts to your data lines, and there's no per-pin protection. So if you manage to put it in backwards, so you clip on the chip and you put it backwards, well, the only thing that's protecting you is the fuse on the board, and that doesn't always work so well. So I do have an alternative. There's a CH347. Now, it is a lot faster, and it usually doesn't have the problem with the board having 5 volts on data pins, but there's still no per-pin protection. One thing that you need to note about these is once you plug into your computer, power is always on, so it's not only powering your chip when you start an operation, but it's always on, so you gotta be really careful when you're trying to connect things. All right, so here is how I usually do my flash dumping setup. So what I have there is a XG-ECU T48. It's safer, so it only powers the chip when you're actually doing an operation, and it also has some things in their interface that makes it easier for you to figure out how to connect your clip. So I also have this clip here. It's a Pomoto clip. Just connects to the programmer through regular hookup cables. The one thing with it is it doesn't have a pin 1 specifically marked on the clip itself. Instead, you have to figure out which wire you're going to call pin 1. So you can see on the chip there, in the corner, there is a little dimple. Usually it's physically molded in there. Sometimes some chips have like a pink dot on it. That may not necessarily be pin 1. So just be careful when you're looking at it. But the rule of thumb is to match pin 1 to pin 1 everywhere. All right, so when I first tried to dump it, I used this setup, but it didn't work. And the reason for that is the CPU is interfering with things. So if you find yourself in a situation where you just keep on getting garbage or you can't actually communicate to the chip, you just try to find a reset pin somewhere. So the reset on this is actually on the back of the board, and it's really annoying to get to. So that's why I tried to not make it a habit to have to reflash this chip. But yeah, once you hold it in reset, it read properly. All right, so let's talk about the CPU a little bit. It is running under the micro NSP architecture. So this is by General Plus, and it stands for Microcontroller and Signal Processor. It's a 16-bit system. It's frequently found in toys and educational learning aids, so toys such as those from Bandai and Takara Tomy. And then for educational learning aids, they're like kids' toys from VTech and Leapfrog and such. So the most distinctive feature about this system is it has a 22-bit address space. Usually you would see 16-bit or 32-bit, but this has 16 plus 6 bits, which is very weird. It has 4 general purpose registers, but for micro NSP 2.0, which is the most common version these days, there are extended registers and 4-stage pipeline. All right. So the assembly format, if you can see on the top right, there's some C code, and on the bottom, it's compiled into assembly. So the assembly format is largely in algebraic notation. So most of the time when you see these, when you see assembly, it's mnemonics, but here you got equal signs alongside the registers. So because there's not so many registers and it has a small instruction set, it actually makes writing assembly fairly fun in a sense. It's not super fun, but it's better than ARM. Okay, so to reverse engineer the flash dump that I dumped, I use Ghidra. So the processor for it is not built in. I downloaded one from Samuel Anderson. Now, when I first got it, it was the decompilation wasn't very good. You can't really read it and make it make sense, so I ended up doing some work on it. So now it actually decompiles to more readable C code. But there's still some issues with it if you're trying it yourself. So for example, there's far pointers. So as I mentioned before, the 16 plus 6-bit pointers, those things Ghidra do not like. As you can sort of see, there's those sub-32 things that are sort of messy. And also, micro NSP doesn't have an overflow flag, but it does have a sign flag. And trying to convert that to something Ghidra understands is not very pretty. So when you see if statements, which I do not have example there, but it does some really weird things in the decompilation. So sometimes you actually end up having to just read the assembly to figure out where exactly is this branch going. All right, so a challenge. When you're loading up the binary, you want to know where it is so that when there's absolute addressing, it can actually go to the correct place. So in microNSP, there's around 3 different ways of doing absolute addressing. So there's function calls, there's goto instructions, and there's switch tables. So in this example, you can see that at the top there is a table pointer going 2003F1, and at the bottom there's what appears to be another pointer. So this one is actually a destination for a jump somewhere. So to try to figure out the addresses, you can try to sort of cut it in the middle. So take the top few bits, and that will probably be your base address, and then mask that off, and then look at the remaining bits. That would be a offset. So put that offset into your Ghidra, go to it, and check if it looks valid. This is valid code, so that's probably fine. Once you figure out whether it's valid, then just move your memory block and there we go. We have code that's in the correct place. You can see that I defined that address as a pointer there, and it points to the function underneath it. So for the chip that's used in the Vital Bracelet, the flash is mapped to 0x200000, and the RAM, peripherals, and OTP ROM are mapped well below this. But in some of the other chips, the flash may be mapped to a relatively low address, in particular ones that don't have OTP ROMs, so they just boot directly from flash. OK, so the GPC4 chip that we have in our Vital Bracelet contains an OTP ROM, but we haven't dumped it yet, and there are a lot of references to it. So how do we figure out what it does? So what I like to do is I just scroll through the different functions that can be located, and then I see if I can sort of map it to some functionality and its call pattern to the device's behavior. So for example, at the initial boot of the device, there's a little intro animation, and there's about 6 frames here. And then I looked through the code and found something that had sort of 6 sections. So each of these sections, not sure if you can see that, but it says draw image. I labeled that afterwards, but it mostly corresponds to that. So we can probably infer that these function calls are drawing images. If you poke around in it more, you can see that it tries to read some data off the SPI flash. And through that, you can figure out how it's actually loading the graphics. So then we can extract the sprites that are in flash, and then we have a reference to what the device is doing. So if you see any call references to this draw image function, you can take its ID, the sprite's ID, and you can use it to infer where in the system this call is being made, and you sort of get an idea of what it's doing at that point. OK, so after going through the rest of the firmware in a similar way, I was able to identify code that wrote to the flash, and with that, modify and patch the code to read out the OTP and write it to flash. So you can see it going through some addresses, it's writing it to flash, and there you go. So now we've dumped the OTP ROM into flash. OK, so now that we have the ROM, we can see the DRM functionality. So most of that is stored into ROM. And we can look at how the DIM signing and the DRM works. So reminder, the DIM is a little card that you plug into the device to load characters from. So their initial implementation of the security is you have a header, and then it contains the vendor ID, product ID, card number, and release date. And only the vendor ID, product ID, and card numbers are signed, and not any of the content. So you can't really make a new card from scratch, but you can replace all of its other contents. So apparently that was a problem for Bandai. So for the next release, they signed the sprites, but it's only the first 4 kilobytes of every 64 kilobytes. That means 93.75% of the data is not checked, so you can just go around those signed areas, place your data outside of it, and adjust the file tables as necessary. The other problem with this scheme is it's using additive checksum. So when you have a bunch of bytes, you just add them all together, and then you take the lowest 8 bits of it. And that can be really easily accounted for. So you have the checksum that you calculate after you change your data, and compare it to before. You have a difference between them, and then you can just spread them out into individual bits into each of the different, a selection of pixels, and you can barely tell the difference because it's off by 1 color on each of those pixels. The other thing it's using is HMAC. So it uses HMAC SHA-256, and the thing with that is it uses symmetric secret. So once a secret has been obtained, it's no longer secure, and that's stored in the OTP, so this scheme's broken. So for the DRM, what it does is it ties a Vital Bracelet to a card. And for the initial releases, you can only use 1 card on 1 device. So what it does is it takes the UID from the NFC chip. So if you know about NFC tags, they all have a UID on it. This one, excuse me. This one just takes it directly and then writes it into the card. So that's all great, but they have a factory test mode, and it has a software test version and a hardware test version, and both of them actually manages to just write into that security slot and then clear it after it's done testing. So they are defeating their own system, basically. So that was also such a problem that in the Digidevice V release, on the second wave, they actually sort of made an emergency update that gated the factory mode behind another special DIMM they had at the factory. So you can't just erase the locks yourself without additional hardware. All right, so let's talk about the NFC a little bit. So the NFC on this is a Integ I2C plus 1K chip. It's dual interface, I2C and NFC. So on the Vital Bracelet side, it'll just read and write the tags through I2C, and on the app side, it uses NFC. So for the transfer process, if you transfer to app, when you enter the menu for connecting, the Vital Bracelet writes the character data to the tag when it enters that mode, and then the app can just read that data out and then write in a command that says it's read the data and to delete the character from the device. Now, from the device, from the app, sorry, first the app sends a command to the Vital Bracelet to check whether the correct DIMM is loaded. So the NFC tag doesn't have enough space to store all the sprites and stuff, so you have to use the original DIMM chip. So make sure that's loaded. The VB will prompt to insert the DIMM and load it if needed, and then the app writes the character data to the tag, and then sends another command to actually commit that character. Security-wise, it uses a tag password, so it's set up in blocks. So on an NFC tag, you would have 4-byte pages, and then this has 16-byte blocks. First block contains version information and the command area, but everything after that is password protected by a 4-byte password. So for getting the password, it's not calculated locally, at least on the app. Instead, it sends your UID to the server, and then that gives you a password. And then for the rest of it, it's also encrypted, so it uses AES-128CTR, and this data is ever only processed on the server. So the app can read the data, but it can't decrypt it because it doesn't know how to. So that gives a little bit of security in the sense that people can't just arbitrarily change their tag contents. But of course, all that logic is also on the OTP chip, the OTP of the device. So it's exposed now. The other feature of NFC here is it uses field detect. So if you put the Vital Bracelet in a field, NFC field, so like a reader or a credit card terminal, vending machine, that sort of stuff, it toggles a pin on the chip itself that indicates that it's inside a field, and the Vital Bracelet would trigger a random encounter. The idea is you're supposed to be battling something that's coming out of the NFC reader, but it's really just a gimmick. You can really just trigger with a button or something instead of having to force people to use NFC to actually trigger. So on this slide, I got a couple experiments. So initially, when I was messing with the NFC, I used an Integ I2C plus Explorer board. So under the phone there's actually a little board that has an NFC chip soldered to it. And then on the other side is a microcontroller that drives the same sort of workflow as the actual device would. And the other thing there is an app that I basically re-rigged a Xamarin demo from. So that's able to send password unlocks and also decrypt the data. And yeah, there's some data. OK. So in November 2022, Bandai released the Vital Bracelet BE, and it's thinner and waterproof. It supports more franchises. And most interestingly, it has firmware upgrades through SD card. So the hardware is still mostly the same. They added a fuse, a load switch, and some circuitry for SD power. The load switch is, if you notice from the first generation, there's actually a power switch. But because it's supposed to be waterproof, all the power stuff has to be inside the device itself. So it's a hardware component that turns the power on and off. So after I got mine, the first thing I tried to do was dump the OTP ROM to figure out the firmware update process. And I modified the code, but it just rewrote a backup copy of the original firmware. So instead, I tried to look at how the ROM accesses flash. So in the bottom left corner, you can actually see I desoldered the flash chip and tried to mount it onto a socket. that introduced some signal integrity issues, so I ended up having to put it back on soldered. All right, so this is a logic analyzer capture from the boot process. So on the first part, you can see it reads some sprites to draw to the screen while it boots, and then it does a bulk checksum across the whole 2 megabytes of firmware. But after that, it starts looking a little bit similar to the sprite signing that I mentioned earlier. So it's checking 4 kilobytes over 64 kilobytes. And on a whim, I just tried the workaround to sort of compensate for that checksum difference, and it did work. So I was able to dump out the OTP from this supposedly secure boot system. So one of the quirks with the version, with the update system is they implemented a version rollback system. So what it does is it copies the new firmware to both main and backup, and then it only does a signature check after that. The problem with this is if you've gotten rid of both copies of firmware, well, there's no firmware, so it's basically bricked. Now, they thought about this, and they allow you to install any new version of firmware. So that also completely defeats their version rollback system. So about BEM signatures, BEMs are BE memories. In this version, there are no device limits, but they added a OTP locking for the content. So they create a set of random bytes that's signed together with the content and stored in the OTP. So this is on the flash chip on the BE memory. There's a secure OTP section. Most people don't seem to know about it, so it's been somewhat effective in keeping pirates away. But the OTP itself is not actually associated with any particular physical chip because there's no get unique ID feature on these chips. So once you know about the OTP and you dump it, you can just copy all that data and then write it into another chip, and you have a clone. Although it seems like not too many people were cloning while the apps were active because that OTP nonce is actually exposed through the NFC interface. So theoretically, people could, Bandit could ban people who are using cloned chips. And it's still not secure because all the HMAC secrets are in OTP, and that's been dumped. OK, so the apps we'll talk about quickly. So there's 3 apps. There's Vital Bracelet Lab, Vital Bracelet Characters Lab, and Vital Bracelet Arena. Vital Bracelet Lab and Characters Lab were the first apps, and their main purpose were to store your characters. So there's only 2 character slots in the system. In the first Vital Bracelet. So any more that you want to raise, you have to put them in the app. There's also some rudimentary multiplayer, but it's not true multiplayer. You fight against Ghost. There's some group battles. Not too much interesting about VB Lab, but VBC Lab is actually an offline version, and they ship with a database. And that, to me, seems to resemble what they would have used on the online version. And instead of using an HTTP server to run all the server-side functions, they sort of just route it through .NET code and run some functions off of it. Now, VB Arena, that's the app that replaced the 2 earlier apps. They use something called GS2, or Game Server Services. But they also have a homebrew API. And that one is a little bit iffy. So they authenticate by encrypting the data, but they don't actually use a user token for some operations. So that means if you know the user ID of whoever, and this shows up on the splash screen, and you can find them on social media because the app is so slow. People keep on uploading screenshots wondering if it's working. You can just take that ID and then submit it to the server and delete their account. OK. Yeah, so VB Arena is a little bit of a mess. The other thing with it is the battles. They don't time it, so sometimes you can get into 10-minute battles. It's kind of annoying. All right, so let's talk about modding. So this is CF O'Grady's DIM modifier. You take a dump of the DIM data, and then you can change the sprites and the stats. But we want to do something more advanced. We want to change the behavior and not just the content. So let's look at some techniques related to that. So The microNSP compiler is a bit verbose. Each memory access tends to generate 64 bits worth of instructions, plus it tends to treat most memory accesses as volatile. But this works to our advantage because there's a shorter encoding for absolute addresses within the first 64K of address space. So we can actually squeeze some space to add our own instructions. So you can see there's 3 assignments there, and I just squished them into 3 instructions instead of all those bunches of instructions. All right, so the microNSP IDE is available on General Plus site. When you make a lot of patches, sometimes it's just easier to write them in C instead of trying to write them all by hand in assembly. So the IDE is available. It has a tool chain, but I don't like their IDE. So the IDE generates a makefile, and I just reworked it a little bit. So now it only does the minimum it needs to compile stuff. So compiling, assembling, linking, and trimming. Trimming is a little bit of an interesting one because what it does is remember that the flash is at 2000000, so it actually makes a file that's that big. So if you want to start inserting things into places, you want to get rid of the earlier stuff that doesn't actually have any content. All right, so when you're writing code, you'll usually want to reuse what's available in the original firmware. There's 2 ways I found to do this. The first is to just write everything as macros to referencing addresses. So they kind of act like variables, but they don't work in all cases. The alternative I found is just defining stubs. So microNSP's linker script doesn't let you directly define symbols, but you can just make stubs that define a function that's empty or a variable that's empty, put it at specific sections, and then the linker is able to resolve them. So the real solution is to actually supply a symbol file from another project. So you compile the other project, it generates a symbol file, and then you feed that back into your current project's linker. But it's in binary, and it's not easy to hand edit, so I usually just stick with this stub solution. All right, making space. So when you want to add new behavior, it's usually the easiest if you just write the new code as a separate function, compile that, and then jump to things. So here I am taking these instructions, and then I just replace them with a call to my new code, and then there's a jump instruction to jump over the other stuff that we're not using. When you do this, remember to maintain original behavior. So that line that's highlighted there, that was part of the original logic. Maintain that if you want things to work properly. All right, and so this is actually the special sauce to my mods. So I built a custom tool that allowed me to simplify building mods. So it can place compiled code into Flash, so the file that represents Flash, and also has a microNSP assembly lexer and assembler that can directly assemble the code, so I don't actually have to copy bytes in from Ghidra. It's currently not open source, but I plan on adding ARM support to it and then opening it up. OK. Well, so here's some of the mods. It's bad Apple. Yeah, and the special thing about this is I actually made it polyphonic, so you can hook up 2 other Vital bracelets, and it'll do 3-channel sound. OK, so the next one is called the Vital Pet. It's a case mod by Veek Design, and it lets you put the insides of a Vital bracelet so it can be handheld like a V-Pet. The part that I worked on is the software. So on the right, you can see I did it together with HeatPhoenix. It's a mod chip, basically. You install it from that chip, and you get slightly different behaviors. So it has workarounds for the heart rate sensor being covered, and also displays the date, which a watch should. It doesn't display date out of the box. It also shows evolution countdown. And this was pretty important because it laid the foundations for my patcher system and for later mods. Yeah, and this was a Kickstarter project. So the next major one is the mod rollup for Vital Bracelet BE. It's considered by many to be an essential mod to the Vital Bracelet BE, and also the most popular. It's got a lot of quality of life features, such as 12 24-hour time, gaining access to exclusive BE memory features, to older DIMMs, and fixing some other annoyances. So we can sort of just look at it getting set. Text bit. Yay, the time has changed. OK. All right, and when Bandai released their major update for the BE, one of the features I made, which when you're checking the evolution conditions, it turns the text yellow if you meet one of the conditions, if you met that condition. It's suspiciously present in their version, so take it how you will. All right, and the last one is a major mod for the Vital Hero. It adds VPET care features such as feeding and cleaning poop, plus a progressively more challenging quest system. The choice of Vital Hero was because it was fairly cheap and easily accessible, well, on Amazon, I guess, earlier this year. So the idea is to make things easy to mod. This was done in collaboration with Comic Munch. So Comic Munch designed most of the logic, and I did implementation, and my special contribution to it is an alarm clock, because, of course, a watch should have an alarm clock, which it does not have by default. All right, so debugging, well, I don't know. So the problem with trying to debug this chip is it actually doesn't have any in-circuit emulation lines. Plus, all their tooling is proprietary, and I don't know where to find a redistributor for General Plus stuff. So the only thing I can really do is stare at the code very hard until I find out where it's breaking. So in the future, one of the things I might try to do is just to implement an emulation of it, maybe in main. So at least then you have a debugger. All right, and that's everything for now. So thank you. There's a QR code if you want to give any feedback. And there's my contact information on right. I'm on Twitter, Blue Sky, Discord. Art's by Adaric. So these slides will also be up on the website, so you can click on the links. And there are 2 more slides after this for links when you get it from the website. And that's everything.
Awesome. Thank you so much. That was pretty cool. We have a bit of time for some questions. If you have any, we have 2 microphones here in the center. You can just queue up and ask any question. Any question, right?
Yeah, any question.
Yeah, any question. So far, we have nothing from the internet. We have no one at the microphone. So while you've been working on all these toys for all this time, what was the biggest pain you experienced?
Well, it's probably debugging, as I mentioned. And, well, trying to not mess up in a way that would make me have to reflash the flash chip. So there's not really a built-in recovery system to any of these, except for the BE. The BE is fine, because you can just load a new firmware from the SD card. But for the earlier Vital Bracelets, if you mess up, you have to reflash it. And as I mentioned before, the reset pin's on the back. So you don't want to do that too frequently.
Right. Oh. Yep. Right. Thanks. And the best toy you've had experiences with, what would that be?
Oh, geez. OK, that's probably my first micro NSP target. It's a boba tea game called Puni Tappy Chan. If you're in the States, it's called Puni Boba Chan. And it has like a clear LCD screen, and then there's a straw that you can move, and you can see it behind the screen. And that was my first, basically, project. And that was really interesting. It sort of got me into toy hacking.
So you saw the pin and then pulled you right in, and then disaster happened, and you spiraled into it. That's awesome.
Yeah, the Vital Bracelet was actually me just trying to find another thing to mess around with. And now I've messed around with all of them. I've collected like all the different firmware variants. There's like 7 of them.
Well, I'm so glad you did, because that was an awesome talk. Thank you for having it. And yeah, that concludes this session. Thanks for your time.
Thank you, everyone.
Give it up.